Bismillahirrahmanirrahim. We will now talk about chapter 5, nth roots and rational powers. And to specify this, we will start with the proposition. So let's give a proposition. Five point one. In this proposition, we are describing the nth root, how we can solve it. So let's say we have late n be a positive integer, so n belongs to z plus if x is a positive real number, then there is exactly one positive real number y such that y power n is x. Now, let's take a positive integer, and if x is positive real number, then there is exactly one positive real number y such that y power n is x. Now, to do this, to see how important this is, we can say that there are x and y in this statement, and we adopt the familiar notation. We can also write or y is x power 1 over n. Okay. Thus, for example, 5 power 1 over 2 is a positive square root of 5. And 5 power 1 over 7 is the unique positive real number y such that y power 7 is 5. Something like that. So, for example, you can say that 5 power 1 over 7 example 5 power 1 over 2 is positive square root of 5, and 5 power 1 over 7 is the unique positive real number y such that y power 7 is 5. And this is according to the above proposition. We can extend this notation to define rational powers of positive reals as follows. So let's define the rational powers of positive reals. Let x is greater than 0. Integer powers like x power m, where m is an integer, are defined in the familiar way, are defined in the familiar way. If m is greater than 0, then x power m is nothing but the product of x up to m times the m copies of x, you can say, and x power minus m is 1 over x power m, and for m is 0, we have then x power 0 is 1. And to show x power 0 is 1, we can write x power 1 minus 1 is 1. Then x power 1 into 1 over x from here is 1. Now, then we can write x over x is 1. Then x and x, they are factors to each other, so 1 is 1. This is true. Now, let m over n is a rational number with m comma n in the integers, and n is greater than or equal to 1. Then we define x power m over n, which is nothing but x power 1 over n power m, or you can even write that nth root of x power m. This is also a notation to write it. So, for example, you can write 5 power minus 4 over 7 is 5 power 1 over 7 power minus 4. Similarly. Now, the basic rules and concerning products of these rational powers are given the next proposition. Although they probably seem very familiar, they are not totally obvious and require a careful proof. So we'll present them and then we'll prove them. The rules for these rational powers. So maybe position 5.2. We say let x comma y are positive real numbers, so we can write them like this. And p comma q belongs to the rationals. Then number 1, x power p, x power q are equal to x power p plus q. Number 2, x power p power q is x power p into q. Number 3, xy power p is x power p y power p. Now, in the basic maths, we use these all the time. Do we know the proof? So let's try to know the proof. One, we first establish the result when p and q are both integers. So let p comma q are integers. In this case, p comma q are greater than or equal to 0. We have x power p is x dot dot x, and this is up to p factors or copies, comma x power q is x dot dot x, and this is for q factors. So x power p, x power q is nothing but these two and product of these. So p factors and q factors, and this is p plus q. And when p is greater than or equal to 0, comma q is less than 0, we get what? We get x power q is 1 over x dot dot x, and this is minus q factors. So x power p, x power q is x dot dot x quotient x dot dot x. This is p factors, and this is minus q factors. And this becomes x power p minus q, and this is going to be x power p plus q. Okay? And similar argument can cover, like similar argument can cover the rest of the cases, cover the other possibilities. That p is less than 0 and q is greater than or equal to 0, and p comma q are less than 0. In all those, the answer is again going to be p plus q, if you follow that carefully. Now, let p comma q are rational. We write p is m over n, q is h over k, where m and h, k are integers. Then what? Then x power p, x power q is x power m over n, x power h over k, which is x power m, x power mh over mk over mk, sorry, nk, nk, and then x power hn over nk. And this is going to be x power 1 over nk power mk into x power 1 over nk power hn. Okay. By the integer case of part 1, established in the previous paragraph, this equals to what? X power 1 over nk power mk plus hn, right? Which by our definition of rational powers is equal to. Now this can be equals to x power mk plus hn over nk, and this can be written as h power m over n plus h over k, and this can be, and this is nothing but x power p plus q. Hence we have established the first results for the pq inside rationals. Now for 2 and 3, now 2 and 3, first is in 1, we easily establish the result for p comma q and z. Now let p is m over n, q is h over k, with m and h k are integers by proposition 5.1. There is a real number a such that x is a power n k, then we can write x power p power q is nothing but a power n k power m over n power h over k, and you can still write this as a power k power n power 1 over n power m power h over k. And then we can write this as a power k power m power h over k, which is again equals to a power m power k, which is power 1 over k, which is power h, and this can be equals to, okay, I should write not like this. And this can be written as a power m power h, which is a power mh. Okay, and we knew that this is equals to x power 1 over n k by the proposition. So now we can write mh over nk, which is x power pq. Right? Number 3 can also be get as, we'll prove the other side. So let's say x power p, y power p is actually equals to x power 1 over n power m, y power 1 over n power m. We can write this as x power 1 over n, y power 1 over n power n power 1 over n power m. And this can be written as x power 1 over n power n. Similarly, y power 1 over n power n whole power m over n. And if you just cancel out this, so this will be x y power m over n, which is x y power p. Hence, we have proved the statement. And let's say something, do some interesting exercises related to this. So one say which is bigger? Which is bigger? If you just look at this and identify, and which one is bigger? 100 power 10,000 or 10,000 power 100? Two is the cube root of 3 or square root of 2. Solve this. You can say, note that 10,000 power 100 can be written as 100 square power 10,000, which we can write 100 power 200. So 100 power 10,000 is bigger. Now 2. This is for 1, this is for 2. Suppose 2 power under root 2, not this notation, let's use the notation 2 power 1 over 2 is greater than or equal to 3 power 1 over 3. Now taking 6th power, this implies taking 6th power, this implies what? 2 power 3 is greater than or equal to 3 square, which is false. Which is false. Is 8 is greater than or equal to 9. Hence, for sure, 2 power 1 over 2 is less than 3 power 1 over 3. Number exercise 2 says that prove that if x comma y is greater than 0, then 1/2 of x plus y is greater than or equal to product of x square root of x plus y. For which x comma y does equality hold? For which x comma y does equality hold? Solution. Let's say we have x plus y is greater than or equal to 2 into square root of xy. If and only if x plus y whole square is greater than or equal to 4xy. If and only if x square plus y square plus 2xy is greater than or equal to 4xy. If and only if x minus y whole square if and only if x square plus 2 plus y square plus 2xy minus 4xy is greater than or equal to 0, if and only if x square plus y square minus 2xy is greater than or equal to 0, if and only if x plus y whole square is greater than or equal to 0, which is true. Not x plus y, x minus y. Yeah. So what is true? Actually, equality holds when x is y. So then equality holds when x is y. Perfect. There we will end this chapter also. Thank you so much.